Hi everybody, welcome to another video in Math 1324, section 2.4, polynomial and rational functions. This section has two parts, polynomial function and rational function. First, we define a polynomial function to be a function of having a single term raised to the n, where n have to be a non-negative integer. So that could be 0, 1, 2, 3, 4, and so on. Domain of all polynomial are all real numbers. Right, but we focus on this. So we just pretty much have all the x2 whole number. Right, so I just have some example here. So we have something like that, x raised to a power, which is a whole number, and then the combination of those terms are constant. Right, so like that. But we cannot have like square root of x. We cannot have that. We cannot have 1 over, maybe have x at the denominator. Let's see. Yeah, we cannot have that either. So cannot divide by x. Cannot have x in the root. And then we cannot have x raised to, let's say, the rational exponent. So cannot have that either. So no radical, no roots, no x in the denominator, and no rational exponents. So we cannot have any of those. Right. The first properties of a polynomial function, because the domain all real numbers, so the polynomial function, the graph will be smooth and continuous. So just continuous. And now first, the behavior of the polynomial. Let's focus on what happened at the end. So look at previous section where we have parabola. So we might have like this, where a is positive. I'll go like this. This is where a is positive and where a is negative. So in this, we focus on the behavior at the end. So here we say on the right side it's going up, on the left side going up, on the left side going down, the right side going down. So we focus on what happened at the end, where the graph going up or going down. And now for that we'll focus on the leading term, actually the one with the highest power term. So it will be this. So with that, the highest power term, the n, the power of that the highest power is the degree of a polynomial, and h of n is called the leading coefficient. So h of n, leading coefficient, n is the degree. Now for every polynomial, we'll just focus on that leading term or the highest power term. I should better write the highest power term. And then focus on the coefficient. If it's positive, the right end is up. If it's negative, the right end is down. So focus on the right end first. If it's positive, going up, negative going down. And then we base on the degree. If the degree is even, they have the same behavior. So we have x squared here, that is even. So the same behaviors, both go up or both go down. If the degree is odd, then they have opposite, one up, one down. For example, if we have like that, then the end behavior, this is positive coefficient, so the right end go up, but it's odd, So one up, one down. So doesn't matter. I mean, we're not concerned what happened in the middle. We know on the right side go up, on the left side goes down. So that's what we focus on here, the end behavior. Right, so just look at this example. So for this, we just look at the highest power term. So to the fourth power. And for that, we focus on two things. The coefficient, which is 3. So coefficient is equal to 3. And that is positive. Now if the coefficient is positive, the right end goes up. Okay, we focus on the right end based on the coefficient. Next, we look at the degree. Degree is 4. Which is even. Now if they have even, so if it's even, they have the same behaviors. Now if the right end is up and they have the same behaviors on the left, so that means the left is also up. Right, so in this case we say the graph of the polynomial, the graph of the function rises to the right and rises to the left. So let me write that out. That's what we have. Let's take a look at the next example. So next example, we have this polynomial. Again, we focus on not the leading term, but the one with the highest power. So the highest power is 5. This sign here is subtract, but always associate the sign to the number behind it. So this will be the highest power term. And so for that, first the coefficient is negative. If it's negative, the right end will go down. So focus on the right end first, which go down. And now we focus on the degree. Which is odd. So if it's odd, we will have opposite behavior. So if the right end go up and we have opposite behaviors, that means the left end, if the right end is down and opposite to the left and right, so that means the left end will be up. So with that, we write the graph falls on the right and rises on the left. That was the left end and the right end. Right. One important thing about this, of course, we can memorize this, but actually to make things even easier, after we find the highest power term, think about this. If we have negative 5 and it is on the right end, x will go to infinity regardless. If x go to the right, it won't be positive. So think about this. If we have negative 5 and we put something on the right which is positive, raised to the 5th power, positive raised to any power, it's going to be positive. Positive times negative 5, so end up being negative. Because it is negative, it will go down. On the y-axis, positive on the top, negative at the bottom. It's negative, so that means it go to the bottom, or go down. So we just focus on the highest power term. On this one, it is not quite easy because we have that and not just single term. So now if I write everything, like that, and we need the highest power term. So of course the long way of this is just multiply this out, take the highest power term, but probably we don't want to multiply that out, so just try to do without it. So we just need a highest power term. So what I do is we just take the term that has the highest power. So for each factor, x plus 1 will take the highest power of that. So we just keep the x, ignore the negative 1, the plus 1. Same thing here, ignore this. Now we have the highest power for each factor, and we just need to multiply all of those. So we have negative 3 x squared, and then an x, and then an x squared again. Alright. So in this way, this we have 2 x's here, 1 will be 3, 2 more will be 5. So this is negative 3 x to the 5th. Right, so that is the highest power term. So we just do that and we have the highest power term. And of course that will be the same as this. So, but we still say the coefficient is negative 3, which is negative. So the right end go down, and then the degree is 5. Which is odd. So we have opposite behavior. So if the right end is down and the opposite behavior, so the left end and right end opposite, so right end is down, the left end is up. So in this case we say the graph going down on the right, so falls on the right. And rises on the left. Right, so that is the end behavior polynomial function. Right, the other polynomial function is the graph of polynomial are smooth and continuous, and the number of turning points for polynomial is at most n minus 1. Right, now think about this. Parabola, we have this, so there's only one turning point. Turning point is where it is changing from going down to going up, from going up to going down. So second degree, one turning point. X cubed might be like this, 2 turning point. So if we have 5 turning point, degree have to be 6 or more. If degree is 7, then we have at most 6 turning points. So the number of turning points cannot be higher than the degree. And so at most will be n minus 1. At most it will be 1 less than that. So n equal to 2. Of course, n equal to 4 might look exactly like that. So maybe at most could be at that values or less. Right. What we actually focus on here is another kind of different things. It's called the regression polynomial. So meaning that what if we have the values, and of course those are not from polynomial function, those not from quadratic. So what we're trying to do is find a function that is best fit to all of this. So what we do is, of course, we can just plot this. If we plot this, let's just do that quickly. I mean, of course, the math we don't have to draw this. Right, let's say it up to 25, so let's say 5 each. Actually, 5 each. Right. 1 and negative 1, x equal to 1, y negative 1, so it's about here. I'm just sketch real quick. X is 3, y is 4. X is 5, y equal to 9. X equal to 6, y equal to 12. X equal to 10, y equal to 25. Of course, that looks like it is on the straight line, but in fact it could be a straight line, or it could be a parabola. Who knows? But of course, it could be either way. We can find a line that fit to this, or we find a parabola that fit to this. But this one we want to find the quadratic function that fit to it. So first, this we have to use the TI-83 or 84, of course, or anything that have the graphing features or advanced list. So what we do is hit the stat, I say edit, and now we'll enter this 1, 3, 5, 6, and 10. Then we go to second list, negative 1, 4, 9, 12, and 25. Right. If we make a mistake, just go ahead and delete. But I don't never highlight the list and hit delete. That is a terrible thing to do. Right. If you accidentally hit that, send me an email, because that's difficult to fix. So never highlight this and hit delete. Right. So we have two lists. At any point, if you want to go back to home screen, you see the quit here, hit second and mode. Right, so we start when it under edit, at enter the numbers, and then second, quick. And what we do is we try to find a function that best fit this. So again, it's under stat, go to calculate, and quadratic regression. X is L1, this one, y is L2, and then we calculate, and we have this quadratic. So the quadratic that best fit all of this, we will write 0.07 x squared 73, that's at 3 decimal places, plus bx 2.075 x minus 3.073. So we have that. So that equation will best fit this data. Right, next we go to qubit polynomial that best fit this. So again, we just enter this list in L1, L2, and we do the best fit. And we'll start again and edit. Of course, you can just enter the number, the data on the top of it, If you want to clear the list, I said never hit delete. Just highlight it and then hit clear and then enter. Do not hit delete, because if you actually hit delete, it will completely disappear on this. So in that case, if you actually hit delete, you have to delete everything else and then go back there and say, okay, I rename this second 3 for L3, and the next one let's put second 4 for list 4 and second 5. So we have to do that every single time. If you actually delete, we have to delete all the list and rename it. Now get back to normal. So again, don't highlight and hit delete, just highlight, clear and enter. That's good. Now we have 10, 14, 18, 22 and 26. And now go to the second 5, 12, 26, 56 and 96. Right. And second quick, hit start again, calculate. Now we want qubit. Now another thing is, if we want to store the answer, we can store in here. Let's say store into a function. To do that, hit alpha trace. Right. Now if you and then say y1. Oh, that's good. Now if your calculator can do that, if you hit alpha and trace, it doesn't do anything. It doesn't pop up this. In that case, try something else. Okay, try this variable, y variable, function y1. So if you are using the TI-83 calculator, or your calculator doesn't do the alpha trace, you have to do that path. Let's try that again. Variable, y variable, function y1. Right, and calculate. Right, and you have that. Of course, you can just write this down or hit y equal to. That is our answer. So let me write the answer here. Y will be equal to 0.004 x cubed plus 0.155 x squared. Try. Plus negative. It's actually just negative 3.944 x and plus 25.236. So that equation would best fit the point. So so probably it will look like this. Maybe something like that. Right. So with that, we go to the next part. The section is rational function. So rational function. Rational function, the way we define it is a ratio. So we have two polynomials and we divide them. So rational function is the ratio of polynomials. So when it is like that, and again, domain is everything that denominator not equal to 0. Right, now some special features is that because the denominator not equal to 0, potentially if it is equal to 0, we may have the break. We will have the break in the function. So in which case, what we have is the line like this, where the function approaching to, in a line like this, where the function approaching to. Of course, this is called the vertical. I'm called the vertical asymptotes, and this horizontal asymptote, where the function approaching to. That's what we define here. Vertical asymptotes. The line x equal to c is the vertical asymptote. So x equal to constant is a vertical asymptote. When x approaching to that number, the function approaching to infinity. So in this case, this is going to be c, because when the function approaching to it, when x goes to it, the function approaching to infinity or negative infinity. When x go to c, the function going to infinity or negative infinity. And to find the vertical asymptote, we do two things. We let denominator equal to 0 and the numerator not equal to 0. The key here is n. So bottom line is bottom equal to 0 and the top is not equal to 0. So for this, we will say it, bottom equal to 0. And we do that first. Of course, there are different ways to solve for this, but let's just use quadratic formula. B squared minus 4ac over 2a. So be 3 plus or minus 3 squared 3 squared is 9 minus 8. So this is just 1 over 2. So we have 3 plus or minus 1 over 2. We have 3 plus 1 over 2 going to be 2. And 3 minus 1 over 2 is going to be 1. So if x equal to 1 or x equal to 2. So that's where the bottom equal to 0. That's the first part of it. Then we go to the second part. The top not equal to 0. Of course we can solve for that, but we already have x equal to 1 or x equal to 2. We just check. We say when x equal to 1, the top will be equal to, now put 1 on the top. 1 minus 2 is minus 1. So it's equal to 1, negative 1, which is not equal to 0. So bottom 0, top is not, so it's good. So we have x equal to 1 is an asymptote. So that's good. Now we test at x equal to 2. The top equal to x equal to 2. 2 minus 2 is 0. Well, we don't want that. We want the top not equal to 0. So that's why this fails. And x equal to 2 doesn't work. So we say it, the asymptotes. Is x equal to 1. Right, so that's what we have. Right, now for this one, what we do is again, we at the bottom equal to 0. Now just solve for it. Of course, quadratic formula works, but for something that simple, don't need to go use quadratic formula just going to plus 4 on both sides. X squared equal to 4. Now we solve for x. To get rid of the square, I'll take the square root on both sides. In that case, we have x equal to plus or minus square root of 4. So that gives us x equal to plus or minus 2. So we have x equal to 2 or x equal to negative 2. Now we check. When x equal to 2, the top equal 2 square minus 3 times 2 plus 2, 4 minus 6 plus 2, that equal to 0. Now if it is equal to 0, that doesn't work, and that doesn't work. Now we check for other values. Negative 2. The top will be equal to negative 2 square minus 3 times negative 2 plus 2. So negative 2 square is 4. That plus 6. 4 plus 6, that 10 plus 12. 2 is 12. And that is not equal to 0. Which is good. That's what we want. And so this is what we have. So x equal to negative 2 is the vertical asymptote. There's only one, so which is the vertical asymptote. Next we have this one. I want to make one tiny adjustment. Let's change that to a plus. Now we start again. Bottom equal to 0. So x squared plus 9 equal to 0. So minus 9. And we take the square root on both sides. And remember, there's a plus or minus here. The reason that the plus minus, I need to explain real quick. I think we talk about that. If we have x squared equal to 9, then we could have x equal to 3 or x equal to negative 3. Because when we square, a positive square is positive, a negative square also positive. So when we have a square equal to a positive number, we will have either plus or minus, either positive or negative answer. That's why there's a plus or minus here. That gives us x equal to plus or minus square root of negative 9. Right. So in this case, what we have here is a negative inside the square root. A negative inside the square root. The answer is going to be imaginary. So in this case, we have no vertical asymptote. Because the vertical asymptote is where the function approaching to when x go to a number. So we need to have a break. We need to have a break in a function, meaning that the function has to be undefined at the vertical asymptote. If we want it to be undefined, the denominator has to be equal to 0. So if denominator equal to 0, there will be a break in the function, and potentially there's a vertical asymptote there. Now I said potentially because what happens if both the top and the bottom equal to 0? When the top and bottom equal to 0, like in this case, when x equal to 2, both top and bottom equal to 0. When that happens, what we have is the hole on the graph. Alright, let me write this down. If denominator equal to 0 and numerator equal to 0, then x equal to c is a whole. At that point. Right. Now let's just graph the function, see what happened. And we graph this. We can just say x minus 2 divide like that. X squared or x squared and so on. But a better way, if you calculate, can do this, hit alpha y equal and then enter x minus 2 on the top, at the bottom x squared minus 3x plus 3. Then we graph. Right. You see, I think I did something. Okay. Right. As you see, at 1 there is the vertical asymptote. They break at 1. But at 2, you don't see anything here. Actually, the graph just look normal there. But actually what it occurs is it's going to be an empty point, empty the hole there. So if you want to just sketch this again, it will have the vertical asymptote at 1. So it go like this. But at 2, it will have an open. That's what happened when both the top and the bottom equal to 0. We have a hole on the graph. Right. Now we go to the horizontal asymptote. Now this will be a lot easier. The horizontal asymptote is where the function approaching to when x go to infinity or negative infinity. So as x get very big, the function will might approach to a constant. So x go to infinity, the function go to a constant. When x go to negative infinity, the function goes to a constant. Right. Now the line y go to d is the horizontal asymptote. Y go to constant is the horizontal asymptote. So x equal to constant. So x equal to something is a vertical line, y equal to something is a horizontal line. And so we define that when x, the function approaching to when x go to infinity. Right, that very clear 3 cases here. When degree on top is bigger than degree at the bottom, there's no horizontal asymptote. Degree on top equal to degree at the bottom. The horizontal asymptote is the ratio of leading coefficient, and when less than y equal to 0 is a horizontal asymptote. There's a saying, I found that online. It said, I said it doesn't have any meaning, but what it does is the abbreviate of this. I'll just spell it out. What it abbreviate, meaning bigger on bottom. We have 0, which is, and then bigger on top, and would mean nothing. And this when exponential or exponents are the same divide coefficient. I don't know who made this up, but I found that online. And there's another way to do this, but let's just focus on this, and then I'll explain a little more systematic and a little bit higher level. Right, so let's find the horizontal asymptote of this. So we just say it very clear. From here we say degree of the top is 2x squared minus 3x, so degree is 2. Degree at the bottom also x squared, so 2. Now degree on top is 2, degree at the bottom is 2, so here we say degrees are equal. So we have degree on top equal to degree at the bottom. In that case we have divide coefficient, so we just divide the highest term, so we say y equal to, we check the highest power on the top, highest power on the bottom, because degree are equal, they cancel out, and we just have 2 over 5. So we have horizontal asymptote is y equal to 2 over 5. Right now, we'll just finish this and then we'll discuss another way to do this. Next one, we have degree on top, x plus 2, so just 1 degree at the bottom. That's why I want to leave the space here so we further discussion. Degree at bottom is 2. So now if degree on top is less than degree at the bottom, so we should say degree at the bottom is bigger. If degree at the bottom is bigger, we have y equal to 0. Very straightforward. Next we have this. Degree on top is 3 because the highest power. Degree on the bottom, x minus 4, so it's 1. So here we have degree on top is bigger. Bigger on the bottom, there's none, so there's no horizontal asymptote. So it's straightforward like that. Right, now that's another way of doing this. So we go back to definition. We want x to go to infinity, and whatever the function approach to a constant, y equal to that constant is the horizontal asymptote. Now keep that in mind. Now think about this. We go back to the beginning of the section where polynomial, the behavior of polynomial only depends on the one with the highest power terms. So now let me look at this. Take the highest power term. Because that's what matters in a polynomial, just cancel out. Now we have 2/5. So indeed, that's what the function equal to, just 2/5, and that's what we have for the vertical asymptote. I mean the horizontal asymptote. Now next on this one, again we take the highest power term on the top and the highest power term on the bottom. We can cancel one of the x, and when it cancel out, we have 1 over 2x. Now, remember the definition of horizontal asymptote is where x approaching to infinity. So think about this. We have 1, just 1. The bottom, x could go to infinity or negative infinity. think about this. If we have a finite amount, for example, let's say we have $1 divided by 2 people, each we have 50 cents. Now, the more we divide by, the less we have. If we have $1 divided by 100 people, each will only have 1 penny. If we have only $1 divided by 10,000 people, we even have less and less. The more we divide by, the less we have, if we just have a constant to begin with. So in that case, at x go to infinity, or could be negative infinity, the whole thing go to 0. So we say y equal to 0 is the horizontal asymptote by definition. Next, so here we take the highest power term on the top and the highest power term at the bottom, and this x cubed over x, that cancel out, and we have x squared. Now, as x go to infinity, infinity square, right? Let me write this out. As x go to infinity or negative infinity, the function will be infinity square, so that also infinity. So the function approaching to infinity. If the function approaching to infinity, we don't have a number. So in that case, there's no horizontal asymptote because infinity is not a number, it's a concept. Right. So that's another way to do it, just based on the highest degree on the top, the highest degree at the bottom. Let's look at an application here. A company that manufactures computers has established this. A new employee can assemble n component depend on t. After the training, t is the days. So find the horizontal asymptote and explain the result. So horizontal asymptote, we just focus on degree on the top. Degree on top is 50t. I'm sorry, the highest power is 50t. Degree on top is to the first power. Degree at the bottom is t plus 4, so it's also 1. So this we have degree on top equal to degree at the bottom. So if degree are equal, we take the high term, and so we have y equal to the ratio of leading coefficient, or we just say 50t over t, where we cancel out the t. We have 50. So y equal to 50 is the horizontal asymptote. So we find the horizontal asymptote. So what is the significance of this? So in this particular problem, t is time, and n is a number of components a new employee can assemble. So we say horizontal asymptote, meaning that mathematically as t goes to infinity, y, in this case n, go to 50, or n equal to 50, if you will. So we say, so that's what mathematically means. So in particular problem, we said as t go to infinity, n equal to 50. So that means as time goes on, so after a very long time, an employee can assemble can assemble 50 components, cannot be more than that. So doesn't matter how much the training goes, there's also the upper limit for that. So doesn't matter how training they have, the maximum they can have assembly is 50 components. So after a long time of training, they can assemble 50 components. Right. Next we'll define a on average cost, average revenue, and average profit. So if X is the number of items that produce sold, then divided by X is the average cost. So if we have the cost of something, produce 5 items, then divide by 5 will be the average cost. Just like that. We actually focused on this more on the Math 1325, but I just have one example. Just make an example here. Suppose the profit is, I'm just going to make the profit I'm going back to be negative. Right. So let's say that is a function for X number of items. Produce and sold. The profit that should be P. Sorry. So in that case, the average profit will be just divided by X. We said the bar is just divided by X. So in this particular case, so either we write like that, or if we want to, we can also write split it up. And reduce negative X plus 50 plus 100 over X. Right. And so with that, we finish section 2.4. Thank you for watching, and see you in another video in Math 1324.